All right, let's settle down. And okay, so let's get started on lecture 19. First, a few announcements. Homework 5 is due today at 10 p.m. as usual. And okay, there's a blackout. Let's not worry about that. So homework 6 will be out today, and the grading for homework 6 will be very relaxed. I'll only grade you for effort. So I have to grade everyone, and you make any attempt to get 100%. But as usual, take the homework as real as preparation for the exam. Okay. And exam 3 is on university schedule. That is Tuesday, December 6th from 8 to 10 p.m. and 8 to 10 a.m. sorry, in Ackerman Grand Ballroom. So we have a big room, so there's only one room necessary. We can even have double seating. And this is lectures 15, 16, 17, 18, 19, 20. Yes, so the discussion around Rice's theorem, and the context-free grammars, and the last 3 lectures on quantum computing. Okay. And because of the strike, I have to adjust the format of the exam a little bit so that the grading becomes feasible. And I have to grade all of the exams because job for 5 people. So it's going to take much longer if we had the old format. So for exam 3, we'll have more weightage to kind of objective questions, the kinds that we had even in exam 1 and 2, the problem 1. But there'll be more weight on those. So these will be like multiple choice, fill in the blanks, true or false, do some things like that. And then between 8 to 10 points for problems, examples being like CFG, plural language is not context free or something like that. Okay. So fewer problems, more objective questions, but again, we're just adjusting as things go along. I'm halfway through grading exam 2, so hopefully I'll be done with them by the end of this week. And also as a reminder, please fill out the official course evaluations. I know many of you filled out the feedback during the course earlier. That was very helpful. Helped me change office hours, kind of told me to emphasize examples more. And the latest poll also suggested, maybe I should do quantum computing. But do whatever you think is right for the course evaluations, but do fill them in. The more input, the better. It's always good to hear what worked and what did not, but just fill them in. So the more evaluations, the more feedback and more information I'll have. Okay. Any questions about the logistics? Oh, there's a couple more. Forgot to say. So homework 6 will have additional problems added in. So I have a plan, regarding what to cover in the last lecture. Depending on how much of it we'll get through, I'll add some additional practice problems as well for you to kind of help you prepare for the last 3 lectures in exam 3. Unlike the previous exams, the last 3 lectures are new to this iteration of the course. So you have fewer practice questions from previous years, but that hopefully is okay. And also, no, someone needs to mute. Let's see. Please mute yourself. Okay, I think the person listened. All right, and also I'll have additional office hours this Friday from 12 to 2, along with the usual ones. So. And this will be in person and on Zoom. Okay. Any questions about the logistics? We just have one more lecture and then the exam on Tuesday. All right. Okay. So if there are no other questions, let's get started with the actual class. So last class, we did a lot of very interesting stuff. We looked at many, couple of very weird things like quantum computers, quantum mechanics tells us happens. And we looked at what a qubit is. We then looked at what's a measurement, the 3 laws of quantum mechanics, just kind of abridged and specially designed with a focus towards our goal, which is to kind of define and see what a quantum computer can do, right? Of course, this is there's a lot more in quantum mechanics than that, but we're kind of picking out the 3 bits that we really need, or qubits that we really need for our quantum computer. Okay, and then we also looked at this EV bomb puzzle that we're going to dig into today. Again, as an example, this as it by itself is not useful for any algorithmic task, but it's very important in understanding or very illustrative of the weird things that can happen when you have these kinds of operations. Okay, and then we've been talking about a single qubit. You can't do much computing with a single bit or a single qubit even. And we'll talk about multi-qubit systems, what's a quantum gate, and hopefully what is a quantum circuit. We'll get to that today as well. Okay. So just as a recap, we had 3 important laws that we were using. So let me just state them again. The first one is on superposition. If you have a system like a photon, which has horizontal or vertical polarization, you have an electron, which has spin up or spin down, whatever they mean. If it has 2 possible states, then it can also be in a superposition of these 2 states. So the state is described by a vector or a pair of numbers alpha beta, such that their alpha square plus beta square adds up to 1, right? And we said we will denote it by a point on this unit circle, especially for a single qubit. It just corresponds with these 2 numbers on the unit circle. Okay. Then we have the measurement operation. If you had a 0-1 measurement device, then when I measure any state psi, what you get is the state collapses to 0 or it becomes 1. It's not a probability that you're seeing. What you see is an actual transformed photon, which is either horizontally polarized or vertically polarized. Only one of those happens. And each one happens with some probability. Okay, so you don't see these numbers or anything. When you do the measurement, all you see is one of these 2 outcomes. Okay, it's like toss a coin, you don't see the probability, you see the outcome of the coin toss. Okay, but the difference, of course, is that they have this negative numbers alpha and beta, and you have this alpha squares and beta squares. Okay, and the third law was that we can build. Nature allows us this amazing ability to do operations on states. Okay, it's not just measurements, but we can also do operations. So we can build a device to do any rotation, meaning I give you a state psi, some point on the unit circle, there's some device which rotates that state. Okay. Similarly, for every line, there is a state, there's a device which reflects the state around this line. Okay. And we were looking at this from sort of high school geometry or 2-dimensional geometry perspective, but that's for the most part enough for the discussions that we'll have. Okay. And the corollary, of these laws is that given any 2 orthonormal vectors, orthonormal means these 2 vectors are perpendicular to each other and their lengths are exactly 1. Okay, we can build a device which does exactly what the horizontal vertical device did for U and V. Okay, if I give it 2 orthonormal vectors, I can build a device which measures in this basis. That's the English way of saying I have this device. When I run a state through this, I get this outcome. Okay. Okay, somebody needs to mute themselves. All right. If you have a question, please unmute, but otherwise, please mute yourself. Okay. All right, any questions about these 3 laws? And if anything is not clear, please ask now, because we're going to use this again and again and again. Okay. And there's this important thing that for 0 or 1, it was just like alpha squared was our probability of seeing the new state being horizontal polarizations. Beta squared was the probability of the new thing being in vertical polarization. For U and V, it's something similar, but you think of it more geometrical. Right? The probability now is the length of the projection squared. Okay, the square will be important, and we'll kind of see some examples as well. Okay, any questions about these things? All right, and then we had this EV bomb puzzle that I kind of introduced for you to think over the holidays. And the puzzle was, some devious mind came up with a device which either is a benign box which does nothing, a dud, or it's an actual bomb, but its fuse is tied to a horizontal polarizing filter, right? So a photon comes in, you do some measurement, happens, and the outcome is 0, it just goes through. The outcome is 1, you get heat, which ignites a fuse, and then you have boom, right? You want to find out, what did the person sell you? Is it a bomb or a dud? Of course, you want to do it without blowing yourself up, right? Obviously, if you're in the classical world, there's not much you can do. You just send a random thing and you'll blow up and find out if it is a bomb or dud, and that's about it. Any quantum ideas? Let's see. So how would you try and decide what you have here without trying to blow yourself up? I mean, think of something, we'll see what happens, whatever it is, right? It might not be the best solution, but let's just see what happens if you try it. Any suggestions? Well, let's see at least, something non-trivial. In the quantum world, we have things in between, right? The first sort of non-trivial stuff is we can send things in superposition. Okay, so let's try and use that. You don't have to send something which is completely horizontally polarized or completely vertically polarized. You can send something which is in a superposition. So what would be a good sort of superposition to try? Any guesses? Let's try plus. Plus or minus both will kind of behave the same. Recall the state plus or plus, it was this guy. Right? Suppose I have a photon in this state and I send it through. Okay. And let's see what happens. In either of these cases, right? Okay. So what comes out in the left side and what comes out on the right side? What comes out on the right side? Any guesses? Well, it's a dud, right? When the photon is just kind of, just goes straight through. So you'll just get the plus state again. Okay, so nothing happened. Right, so, but what happens on the left side? Any guesses? Well, we know the laws, right? So when I pass it through the horizontal filter, it collapses to 0 with probability half, or becomes 1 with probability half, which then ignites the fuse. And you have boom. Okay. So meaning 50% chance you'll just blow yourself up. Okay. But 50% chance what comes out is a 0 on the left side, whereas it's a plus on the other side. Okay. So at the very least, 50% chance you see a difference between the two sides. Okay, 50% chance you didn't get blow up. I mean, you didn't blow up, and there's a difference. Okay, so that's the difference from the classical world. If I just send a random, if I had like a 0 or 1 polarization only, right, the chance of blowing up is still 50%. But when you don't blow up, you don't see any difference between the two sides, right? Here, 50% chance, you don't blow up, and there's a difference on what comes out. Okay, yeah?
Could we send in a photon with like extremely small?
We will in a little bit, but we have these two things, but remember, how do you know which is which? We still have to do something to know what happened. You have this photon coming out, but you have to probe it to decide, is it 0 or 1 again, or 0 or plus again, right? So how can I do that? Any suggestions? So, something happened. I just got this new photon, which is either horizontally polarized or is kind of at this 45-degree angle, but I have to detect it somehow, which case I am in, right? So how can I do that? You can put a vertical filter. Well, let's try that. Suggestion. Put a vertical filter. Okay, so you basically, what you're doing is, okay, I'm going to sense plus, and then whatever comes out, I'm going to put a vertical filter. Okay, or in other words, we can make it simpler and just say we are doing a measurement in, let's say, the 0-1 device. Okay, so I do this measurement. So we have two cases to figure out. So case dud. So this is the experiment. Someone gave us a box. I'm going to send the plus photon through and then see what happens when I put the measurement device after that. Okay, that's my physics experiment. You gave me the box. I'm going to send this photon, put this measurement device, and see what happens. Okay. So if it's a dud, then what comes out is still plus. Okay. And if it's a plus, what's the outcome here? Final readout is 0 with probability half, and 1 with probability half. Right? Plus is 1 over square root 2 times 0 and 1 over square root 2 times 1. So what comes out is 0 with probability half and 1 with probability half. Okay, so kind of, maybe something happened. Let's see. What happens if this was a bomb? If this was a bomb, what comes out is not plus, but 0. Okay, so in this case, final readout is 0 with probability 1, 1 with probability 0. Okay, there's a condition here first, right? Wait. Whoa. Okay, let me maybe just write it down. So if it's a bomb, two things happen. One, 50% chance. Okay, this cannot be avoided, right? That branch of the universe, we exploded, nothing happened. 50% chance what goes through is in 0. And then on top of that, you have something. Okay. So, this is all chance, right? Here, 50% chance we didn't blow up, and after that, we see 0 all the time. There, we see 0, half, and 1 half. Okay. So, there's some chance we will detect it, right? We will detect it when kind of you end up on the one side here, right? Otherwise, you don't detect it. Okay. So can anyone tell me what's an issue here? Other than the explosion. I mean, explosion, okay, is 50% you're dead. But the other 50%, you want to say you learned something, right? But if you get a 0, you don't know if it was actually a 0 because you didn't explode and then the experiment actually said a 0, or if it was a dud and you just came 0 because of 50% chance, right? So what's one way to kind of slightly modify this experiment, which is giving us some information, but I would say not the best possible way to use the idea. Yeah.
I'm not really sure how, but I guess we want to aim to so that the case dud is 1, 1 with probability 1, I guess.
Something like that. So, the ideal thing would exactly that, but the one way to do it is, just do the measurement in plus minus basis. That we have a device which can also detect whether it's not just horizontal or vertical, but is it 45 or 135, right? We can do that, yeah? Not the vertical filter, but the measurement device, or the horizontal vertical polarization measurement device. Remember, if we send a photon through it, it comes out as 0 with probability something and 1 with probability something. Okay, so we are using that. Okay, so the suggested modification is, instead of this, maybe put a okay, so I'm going to put this measurement device next and see what happens. So this is my experiment now. I'm going to send the plus through the box, and I'm going to measure in the plus minus basis. Okay. Now we set up the experiment, so we can reason about it pretty mechanically. We'll do a same case analysis. If it is a dud, what happens? Well, when I send it through, nothing happens, and just plus goes through. So you're measuring in plus minus device. So the final readout is plus with probability 100%. Right? So recall, if you have the two bases, it's measured by the angle. And if I'm sending plus, its angle with plus is, perfect alignment. So you just get 100%. Okay. I think we did these calculations last time too, right? Where'd it go? Okay. So this was the H device that we called. So we're using that. And if it is a bomb, what happens? Well, 50% chance, you blow up. So 50% chance you just exploded and the experiment ended with a very bad outcome. 50% chance, no explosion. So you send in plus. Okay, so no explosion, you got lucky, but what comes out here is a 0. And now we're putting it through the plus minus the H device. Okay. And what does the H device give us? So if I send in something in in horizontal polarization through the measurement device with just plus and minus, what would the outcome be? Yeah.
50%.
Exactly, right? So it's if you think about it geometrically, the two vectors for us are this is plus and this is minus, right? And whereas 0, it's bang in the middle. Okay, so its projection lengths on these two things are exactly 1 over square root 2 and 1 over square root 2. Okay, so what you get is plus with probability half minus with probability half. Okay. So in the case of a dud, you will always see plus with probability 100%. In the case of a bomb, if you change these two events, something bad happens, explosion happens, but with probability 1/4, you'll actually see a minus. Okay. Yeah.
So during the bomb filter, are you saying that like when we send in a 0 vector that we have a 100% chance of survival?
If we send in a 0, yeah, we have 100% chance of survival.
I think then the next logical step is just like keep sending in zeros because there's no risk of that, and then you try and measure with your H device.
But then, there's no risk, there's no gain. Right? So if you only send in 0, you only get 0. But even in the case of a dud, you'll get a 0 as well, right? So how do you distinguish between the two? So we have to identify a scenario where the chance of explosion is small, but then there is this counterpoint, right? But the two things react differently. We can make the chance of explosion very small, but when they do that, both are doing the same. Okay, so somebody want to poke the bear without actually waking it up, right? Okay, so in conclusion, so what's the summary? When we do this experiment, if bomb 50%, we explode. Okay, 25%, we don't learn anything. Okay, so 25% chance we didn't explode, but then the final H device also said a plus, which is also what the dud always says. So you didn't learn anything, both gave you the same result. But 25% chance we detect it. But well, at least you made some progress, right? 25% chance you actually detect there is a bomb without any explosion. Okay, I mean, this is already something that is not at all possible classically. Okay. So 1/4 advantage of actually figuring out there is a bomb without triggering it. Okay, that is quite counterintuitive, right? Imagine it was not in superposition. If you're not allowed to send in superpositions, there's no way you can do anything like that. Yeah.
Can you explain how the H device helps here? My understanding is that we still have a 0 and 1 with probability 1/2, and then somehow that turns it into a plus all the time.
No. So okay, so when you send in a 0 through a plus or minus device, it can come out as plus with half the time, and it will come out as minus half the time. So you can have both of these things. Okay, that's what's happening in the bomb case, right? But in the dud case, when you send in a plus, it goes straight through. So it's a plus, and it's always a plus. Okay, so you detect it 25% of the time. Okay, any questions about this? It's quite counterintuitive that you can do it. And the main thing we're taking advantage of is that when you send something in superposition, the state transforms when you do the measurement. Okay?
So with the bomb or the blocks, we're not supposed to measure it, right? Like just send it through anything called the block.
Yeah, I mean, so that's the way the horizontal polarization device works, the horizontal filter works, right? It does the measurement. If it's a 0, it just sends through. If it's a 1, then it generates heat, which then triggers the bomb. Okay, there are measurement devices, and there are filters, right? So a filter is something, if I send in, some any photon, then it first behaves as if it's doing a measurement with the 0-1 device. And if it's a 0, it just goes through. If it's a 1, it becomes heat. Okay, and we tied the bomb to the filter as a fuse. So when we send in something, with probability, if you send something in a state alpha times 0 plus beta times 1, with probability alpha squared, the 0 just goes through. Probability beta squared, you will just get an explosion. Okay, that makes sense.
That's like 1 photon, right?
It's 1 photon, and in one case it's becoming heat, in one case it is going through. You can think of it as maybe 2 steps, right? This is how we define the horizontal filter. If I send in psi through it, which is alpha times 0 plus beta times 1, then you will see a 0 with probability alpha squared. And nothing, or there's no light, but the light has been converted to heat with probability beta squared.
So if you had like an infrared camera,
Yeah, if you had an infrared camera on it, you could say that's one way to cheat, maybe. Okay, so I mean, this is actually something, if anyone has your UV polarizing glasses, it's exactly what's happening on those things. That device exactly does this. It sends, some of the time it just becomes heat. Heat is something that, it's small enough that we can't detect it, but the loss in light is something that we notice physically. Okay.
The filter does cause it.
Yeah, the filter does cause the photon to either disappear, or it sends it through, but you always send it through in the state 0. Okay. Any other questions? Okay, so we made some progress. It's something which was not possible without superposition. We are able to make some progress. We can detect it with probability 25% instead of 0%. Okay, and now we can increase it to 99.99% or whatever we want. Okay, and this was suggested already. So let me just kind of jump to it. Okay, so what we're going to do is first, so someone suggested, instead of sending in 45-degree angle, send it at a slight angle so that you decrease your chance of explosion noticeably. Okay, so let me send in something. So pick a number n. So let's say it's 1000. Okay, and let epsilon be pi by 2 times n. Okay, so essentially, this is our 0, this is our 1. I'm picking something at an angle epsilon here, tiny angle. And the point is, as the angle decreases, you increase the chance of just going straight through, even if it's a bomb, and you decrease the chance of an explosion, even if it's a bomb. Okay. All right. So the new thing is a very clever solution. So you send in this state psi, which is cosine epsilon times 0 plus sine epsilon times 1. Okay, so most of it is kind of, tiny angle. The length, the x coordinate is cosine epsilon. The y coordinate is sine epsilon. Okay, that's the photon I'm sending it through the first time. But then what I do next is, I guess you could do it, maybe before or after. Let me do it after. I don't think it matters. I'm going to build a device that rotates by r epsilon. Okay, rotates whatever comes out by epsilon. Okay, so rotation divides epsilon. So recall, as I said, nature allows us this magical ability to change states by rotation. Okay, so I can build a device which, for any angle, epsilon and theta, whatever you have, I can build a device which rotates the state on the circle by that angle. Okay, so that's all I'm going to do. So I'm going to send this. Let me put it in front. I think it makes it easier. A bit more streamlined. So let me just. Okay, so I'm going to send just the 0 photon through this device, rotation by angle epsilon. Okay, I'm not doing any measurement. I'm just performing this operation which changes the state. Whatever comes out is going to be fed into the box. Okay, and whatever comes out, I'm going to loop it back through this. Okay, so every time that the photon comes out, whatever state that is in, I'm going to loop it back to this rotation by epsilon device. Yeah.
You can't do this infinitely because the photon, I assume, loses some measure of energy over time.
I mean, here we're working in the case where everything is reversible, right? There's no energy loss here. Okay, like let's say you're doing this in experiment in vacuum, then there is no loss. Okay, and you can think that basically loop it back n times. Okay, so this is my experiment now. Someone gave me this box. I just keep the box in front. I send this photon through this rotation by angle epsilon device. It goes through. I bounce it back. Send it through the same thing again and again and again. I'll do this bouncing through n times. Okay, so rotate by epsilon, send through box, repeat n times. You can recall, we chose epsilon to be something like 5 by 2 times n. Okay, so that's my algorithm. Except after I do all of this, I need to mention what's the end. Okay, in the end, measure in 0. Okay, so this is my experiment. He gave me n, which is 1000. I'm going to do this 1000 times. Rotate by epsilon, send it through the box, whatever comes out, rotate by epsilon, send it through the box. And then in the end, after doing it 1,000 times, I'm just going to do a measurement. Okay. Is a physical thing clear what we're trying to do? Any questions? Okay, so again, once we set up the experiment, we can check what happens, right? So let's do a case analysis. If the box was a dud, okay? So if the box was a dud, initially I'm sending in 0. I rotate by epsilon, send it through the dud box, which just goes through, and then it comes back, right? So what comes out here? Here, let's do the first loop, okay? So first iteration. What state is the photon here? You just rotate by epsilon, right? So the state here is cos epsilon times 0 plus sine epsilon times 1. Okay. What comes out here? The same thing. You didn't do anything. It's a dud. It doesn't change anything. There's nothing in the box. Okay. So if you think of it as a point on the circle, what happened? You started with 0. Once you get here, you are in a tiny epsilon away. What happens the second time? What happens the second time? So we're not doing any, the only non-trivial thing that's happening is that every time you're just rotating the state by epsilon.
So it's just another slice.
Another slice, right? So you're just going to go here, 2 epsilon, right? As I said, the rotation device is kind of powerful, right? Because whatever state you send in, it does the same operation. Just move it along the circle by epsilon. If I send it in 0, it changes it by epsilon. If I send it in angle epsilon, it moves it further along by 2 epsilon, and then further along by 3 epsilon, and so on, right? So third iteration, where am I going to be? I'm going to be okay. So every time I'm just increasing the angle a little bit. So after n iterations, what state am I in?
Any?
N times epsilon, but we chose epsilon to be pi over 2 times n. Okay, so after n iterations, you're at angle n times epsilon, which is exactly 90 degrees. Okay, so after n iterations, you're exactly in this vertical thing. You just rotated it every time slowly, 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 slowly. You ended up in the vertical stuff. All right. So now we measure with plus minus, so not plus minus, but 0, 1. So what happens then? I'm sending something which is, basically 1, right? It is perpendicular. It's 90 degrees angle with the 0 axis. So what happens when I send it through the horizontal measuring device? What comes out? What do the laws of QMs tell us? Yeah. We're going to read 1 every time, right? With probability 100%. Okay. And here it will be 0 with probability 0. Okay. So the main non-trivial thing that we're using is, I mean, maybe not even non-trivial thing, but we're using the fact that the laws of probability, laws of quantum mechanics have this behavior that when I send in one outcome happens with probability proportional to the length projection square. Okay. This is again 2. Right. Okay, so the dud case, we kind of know what exactly happens. Right, so summary, if dud, final readout is 1 with probability 100%. Okay, if I do this experiment with a dud box, I'm going to end up with 100% of the time, no questions, right? And let's now analyze what happens for the bomb case. Right, so we have the bomb. And what's our experiment? We send in start with 0. Then we have the rotation by epsilon operation, send it through, whatever comes out, we loop it back. Okay. Let's do first iteration. Let's just work through, some trigonometry and figure out what happens each time, right? So maybe I'll, any guesses what happens? What do you gain out of it? Yeah.
The filter will always polarize it back to 0. So every time you come back, it'll always insert like an epsilon rotation.
Exactly, right? So the big gain really is that when it was a dud, the operations were always kind of piling up. You're rotating by epsilon, and then again by epsilon, and then again by epsilon, and then again by epsilon, right? But when you have the bomb, whatever comes out is always in the 0 polarization, if it doesn't explode. If it explodes, then you're dead. But if it doesn't explode, then you're in 0. Okay. But we have to figure out, why is this better than before? Why is it like, maybe helpful to do this small angle and not explode? Okay. Well, let's see. So you start out with, let me draw a picture. So this is the state of the starting photon, right? Here I'm in this state. Here I'm in slightly rotated state, right? So this is epsilon. Okay. And now 2 things happen. With and here, kind of my universe splits into 2 possibilities. What comes out is reset to state 0, or I just have how do you say it? Kaboom. Okay, so you're in either of these 2 cases. But the point is, like, somehow you reset it back to where you started. Okay, and this happens with probability. So what is the probability of the first case and the second case? What's the probability that you just see is 0 again? Again, use the loss, right? If I have the horizontal filter, the probability that you see is 0 is alpha squared, if I have point alpha beta, right? So this is exactly cosine squared alpha. And the probability that you're an explosion is sine epsilon whole squared.
You said cosine squared alpha. Did you mean cosine squared epsilon?
Cosine epsilon whole squared, sorry, yeah. Okay. We're using the same law again and again. If you have alpha and beta, when you put it to the device, the probability that you see one outcome is alpha squared, the other one is beta squared. Okay. Now, how small is epsilon? Epsilon is very small, right? You say it's pi over 2 times n. So n is 1,000. It's pretty small. Okay. And here's some. So again, you repeat it second time, right? But the second time is the same thing that's happening, right? Either you exploded and the experiment ended, but if it did not, you did not explode, then what you're sending in is back in state 0. So the same sort of thing repeats. If no explosion, same thing as before, right? Because what I'm sending in is exactly in so the same thing happens again. You go from 0 to epsilon, and then you go through these 2 states. Either you explore with probability sine epsilon whole squared, or you go back to 0 with probability cosine epsilon whole squared, and then you keep repeating it. Okay. And so far, so good. And the main gain, and this is something which actually helps a lot in quantum computing. What is sine epsilon like? How does it grow with epsilon? If n is like 1,000, then I have my angle is 90 by 1,000. It's a very small angle, but what is the sign?
Positive.
It is positive, but how small is it? Yeah. Right. So for small angles, you can really sine epsilon is less than epsilon. Because the number is at most epsilon. Okay. You can do this by the Taylor series or whatever, but we only need the simplest inequality here that is like epsilon minus epsilon cubed or something. So it's at most epsilon. Okay. So what does this mean? The probability of an explosion is pi by 2 times n whole squared. Okay, let me put this in big thing. Okay, so the probability of an explosion is, if n was 1,000, the probability of an explosion is like 1 in a million. Almost. There's a pi, it's like 1.14, so maybe slightly more than 1 in a million. But basically, the probability of explosion is really small. It's 1 in a million instead of like 50% in an earlier experiment. Okay. So each time I run it through the box, the chance of explosion is something like pi over 2 times n whole squared. So I do it n times. I do it 1,000 times. So what's my chance of a total explosion? So each time probability explode is okay, which is something like I think I can check it. It's 0.000. It's this small, this probability that I explored when n is 1,000 is this small. Okay. It's as if I tell you you're crossing a road, every time you cross it, you'll get hit with this much probability, but you have to cross the road 1,000 times. What's the chance that you survive, or what's the chance that you get hit? 1,000 times this, right? You know, it's at most 1,000 times this. Okay. So implies probability we ever explode is at most n times pi by 2 n whole squared, which is something like okay. So in our entire experiment, we will only explode with like 0.00247 chance, really tiny chance. Okay. So with 99.997% of the time, we are not going to explode. Okay. And what happens when we don't explode? If we don't explode after n iterations, what state is the final photon in? 0, 0, right? Because every time you don't explode, it's being reset to 0. That's the horizontal filters modus operandi, right? It either generates heat. If it doesn't generate heat, it resets it to 0. Okay. We are in state. Okay. And we call our experiment after n iterations, we measure it. Okay. So what happens if I measure the 0 state in the 0, 1 measurement device? So if bomb explode with probability less than or equal to n times whole squared, or in okay. So either we're going to explore, or it happens some of the time, which is, or we're just going to say we are in state 0. Okay. So we have perfect separation when we don't explode. In the case of a dud, we're in 1 with 100% chance. In the case of a bomb, we're in 0 with 99.997 chance. Okay. So it's amazing, right? We're basically saying either you exploded with 0.0025% chance, or when you didn't explode, you have this perfect separation between the two things. Okay. So experiment we explode it's not even percent, it's actual probability. So if you do percent, it's even less, I guess. So we are going to detect that there is a bomb with very high certainty without any explosion. Okay. Does the entire device make sense? Again, this is as we will see, this is a very, very simple kind of quantum circuit. where you have the simple rotation operation and the horizontal filter that is being looped again and again. Okay. Now, when we talk about quantum circuits, it's going to be similar. You have different rotation objects stacked on top of other. Okay, every time you stack, something non-trivial is happening, and that is going to separate classical circuits from quantum circuits. Okay, as we will see and talk about, this is like a simple example of a quantum circuit, and we'll talk about more general things later on. Any questions about this? I mean, as I said, it is counterintuitive, right? It's something that we do not think is possible. That if I give you this bomb, how do you detect it without exploding? Quantum mechanics tells you can. For whatever reason, nature allows us to do these operations. We can't ask why these things are true. Those are the laws. We just have to live by them.
The similarity between filters and the measuring devices.
So measuring device do not destroy it, right? They always send the photon through in one of the two possible states. Okay, and the filter is something, again, you should think of it as a different, it's kind of two devices put together. Let's say, first it measures, and if it's one, there's something which converts it to heat. Okay, so I mean, there's something physically possible that we're assuming, which is I can convert light to heat. Okay, and that's the physical device that someone gave us. In fact, any polarizing lens is exactly that.
Okay, so the state is like, but like through both, the state can still be superposition. Like if the filter is like maybe a plus filter, then the outcome can still be a superposition.
No, if it's a plus filter, it either always sends it out as a plus or it generates heat.
Okay, but the plus state is itself a superposition.
Position of 0 and 1, yeah.
Okay.
Yeah. Sure. Okay, so whoever is the host, can you make me co-host? I need somebody to make me co-host. Okay. Who's the host? Yolanda, can you make me host? Hold on 1 second. I need to fix the Zoom.
Yeah.
Okay, people on Zoom, I have to end the meeting and restart it. All right.
We can try moving this.
I think it was closer last time. It doesn't fit. The space is not big enough for the.
That's why I thought the extension cable thing.
All right, I think we're all back online. Hopefully the folks on Zoom can hear me and the class is being recorded now. Okay, let's get started. So what did we learn? Okay. So I would say the main thing we learned is composing operations, right? In which in our case was rotation devices.
Is this the theoretical maximum probability of detecting the bomb?
You can show something like that depending on how many uses you allow of the bomb, of the device. If you charge somebody like $1 for every time you can use the bomb or the device rather, then you can show something like this. It's not trivial to show, but you can. It's a good question. All right. And okay. Okay, so the main message of this seemingly silly puzzle is that you can compose operations, in this case rotations, and it turns out to be quite powerful. Okay, that's number one. And this is minor sort of very mathy detail is really helped this whole thing. Okay, which is that sign of epsilon is pi over 2 times n, but then the probability of the outcome is the square of the amplitude, right? It's beta squared and not beta, okay? So it became, instead of being 1 over n here, the sign is like 1 over n, but then the probability became 1 over n squared. All right. And in many quantum algorithms, the square is really what comes down to save you. Okay, there's something called Grover search, where the square is kind of, again, shows up. It's kind of something that tells you that quantum computers can be quadratically faster than classical computers. Okay, for some tasks. And again, there also the same kind of thing happens, where the square in this probability comes down and saves you. Okay, so that's why I like this example. It kind of illustrates the two things. One, composing kind of gives you non-trivial power, and then the square kind of, the fact that there's a square in the amplitude and the probability really helps you as well. Okay, all right, but now we can try and build on this. Okay, so far we know how to operate on a single qubit. Okay, but as I said, quantum computers and single qubits are not very useful. So let's try and go to more general things. Okay, so my goal for the remainder of this lecture is to basically define what a quantum gate is. Okay, and to do that, we have to first talk about things which don't just operate on single qubits, but on multiple qubits. Okay, so this involves some notation, which we will, which I think is very helpful in kind of keeping the bigger picture in mind and not getting lost in the weeds with all this, carrying all these alphas and betas around. Okay, so we'll talk about qubit. These are great with names. So a qubit is basically a system with 3 possible options. We had an electron which had up or down spin, 2 options. We had a photon which had horizontal, vertical polarization, which is two things. And there are some physical analogs where there's a system which has 3 possibilities. Okay, you can denote them as 1, 2, and 3. And you can have more generally, you can say there's a system maybe with 4 options, with 5 options. More generally, you have something called a qubit, meaning it has some d number of options, and as d changes, you get different systems. All right. So you have 1, 2, 3. Qubit is a system with d possible options. Yeah, again, we'll denote them as 1, 2, 3, so on.
Why aren't these 0 indexed?
That's a good question. You should, I think it becomes a little messier combined with the linear algebra notation. Okay, you can think of it more. We will use 0 indexing maybe for the variables, but this is like the alphabet. That's kind of the analogy. So it helps a little bit not to think of it right now. Okay. Okay. So to talk about this more general things, we need some notation which makes it very convenient to talk about these things. Okay. Some extremely useful. Okay, who here remembers high school vector algebra? If you're in high school and you had to write something about a vector, like let's say maybe -2, 1, and 3, 3-dimensional vector, how would you write it? Or one of the ways that you learn? Yes. So you had this -2 times I plus 1 times j plus 3 times k, right? You had the special sort of symbols to denote special vectors, and then So I was basically 1, 0, 0. J was meant to denote 0, 1, 0, 0, 0, 1. I don't know why they do it, but this is one way it's taught, right? And of course, if you're an undergrad, you don't call them IJK, you call them E1, E2, and E3. Okay, so again, you're just calling these vectors by different names, right? I'm calling this E1, you're calling this E2, I'm calling this E3, right? So now V becomes -2 times E1 plus 1 times E2 plus 3 times E3, right? So E3 is supposed to denote the vector 0, 0, 1, E2 is supposed to denote 0, 1, 0, and so on. There is some advantage to doing E1, E2, E3, etc. instead of IJK. What's the advantage? Well, you can talk about even 27-dimensional vectors instead of only running out of names at the end of the English alphabet, right? So if I have a vector with D coordinates, you can think of D as like 20, 100, 10, 24, or anything like that. So I have a long vector. Don't worry, we don't need too much of this. We just need the basic notation. We can write it as like, if this was alpha 1, alpha 2, up to alpha D. You write this as alpha 1 times E1 plus alpha 2 times E2 plus alpha D times ED, where, it's the natural generalization. So E1 is 1 followed by zeros. E2 is 0, 1, and all zeros, and so on. You're picking the same vector, either you write it in the coordinate system or you write it as some of these individual vectors, E1, E2, and ED with some coefficients. Okay. This is, we moved up from high school to undergrad, where we can talk about higher dimensional vectors. All right. If you're a quantum undergrad, meaning you're studying quantum computing or quantum mechanics, then how do you denote these vectors? Well, instead of using E1, you use the ket notation. That's the only thing. Okay. All right. So, one with this weird bracket, this is called a ket. Kind of half of a bracket is basically you have this line with this greater than symbol that's meant to denote a vector. Okay, one is kind of like E1. There's 1 in this one coordinate and 0 everywhere. If it's a 2, then it's 0 and 1 followed by zeros. 3 is like 0, 0, 1, and so on. Okay. The advantage about talking about these things is that you never have to figure out, okay, is it, which is it? Is it 1, 0, 0, 0 or 0, 1, 0, 0 or anything like that? You kind of work with them abstractly. The only thing you will care about is some properties of them, as we will see. Okay. So this is called a ket. And this was introduced by physicist Paul Dirac long ago, and it's called Dirac notation. I used to dislike it because you have to kind of reinvent everything that you knew already in this new notation. But once you start doing quantum mechanics or quantum computing, it's really, really helpful, especially for quantum computing, I think. Okay. And you should always think of it as a column vector. All right. Yeah.
So does that mean that quantum computers are more than binary? They're denary?
They will be, it's somewhere in between. Okay, so there's a difference in that, when we think of computers, classically we think of everything as bits. But when you have multiple bits, it doesn't really change much. You're operating on each one separately. In quantum mechanics, when you have multiple qubits, in some settings, you have to think of them as bigger, like qubits instead of individual bits. Okay, we'll talk about that a little bit. Okay. As I said, we're going to look at very simple Ds where it's not really like arbitrary dimensions, but it's basically multiple qubits put together is one higher dimensional vector. That's the abstraction that we have to get to. Okay, good question.
Like bits and bytes and kilobytes.
Exactly. Yeah. Any other questions? Okay. So far, we just had this notation. Now comes the most. Okay, so the most important operation in terms of calculating and understanding what's happening in quantum computing and quantum, mechanics really is, any guesses? Well, it's what dictates the laws, like, it's what allows us to compute these probabilities of outcomes, what happens if I do this measurement, what happens if I compose these rotations and so on. It all comes down to some math. So if I have two vectors, u and v, then I have the dot product between them. Right, it's also called inner product and whatnot, right? So these are, let me use coordinate system first. You have u1 and u2. These are the two coordinates. You have v1 and v2. These are the other two coordinates. Then u dot v is u1 times v1 plus u2 times v2. Okay, so I'll give you two vectors, two dimensions in this case. Then the dot product is sum of the coordinate-wise products. Okay. And in d dimensions, you have something similar. Okay. So, for example, let's say u is 0.8, 0.6, v is maybe 0.6 and 0.8. What is u dot v in this case? It is okay. And you can also have, similar things for, let's say, what if I have minus 0.6 and 0.8? Then what is u dot v? Comes out to be 0. Okay, that seems perfectly cast. All right. And what is u dot u of a vector? It's magnitude. It's length squared. Right, so it's usually denoted as the length of the vector squared. Okay, it's the square of the length. Okay, and there's also a geometric view of dot product, which is critical for us. And what is the geometric view? If I have two vectors, let's say u and v. Okay, again, think of two dimensions. We're only talking about two vectors. You can always think it's in two dimensions. And let's say their angle is theta. The angle that they have between them is exactly theta. What is u dot v in this case? there's a way to write down the dot product just in terms of this angle and the lengths of the vectors. Okay, so in particular, it's the length of u times the length of v times cosine theta. Okay, so if the angle is theta, the dot product is exactly this. All right, and in a more specialized form, if u comma v are two unit vectors. Okay, again, think 2 dimensions. These are two vectors whose lengths are exactly 1, right? So meaning they are on the circle. So this is u, this is v. If the angle is theta, okay, then what is u dot v? It's, what's the length of u? 1. What's the length of v? It's 1, right? So it's exactly cosine of theta. Okay, so it basically comes down to the length of the projection, right? The projection here by Pythagoras' theorem is exactly cosine of theta. Okay, so is length of the projection of v onto u. Okay, there's a sign sometimes, but let's not worry about that further. All right. So what does this tell us about where is our, okay, so hold on, let me do one more thing and then we'll get to it. So this geometric view is very helpful in actually computing all these probabilities, as we will see. But to write down those things, it's helpful to have one final notation. Okay, and this is where the utility of Dirac's notation comes in. So if you have two vectors, u and v, right? We said we'll denote vectors with this weird braces. Then the dot product is kind of denoted as this inverted things. Okay. So when the left-hand side here is called a bra, and this is called a ket. Okay, so that's how thank Dirac for it, I guess. But the notation helps us kind of write down inner products and compose them in some way. Okay, so I have two vectors u and v. The inner product or dot product will be denoted with these two pointy brackets with this line in between. Okay, it's called a bra and ket. So you should think of bra as like row vector, this as a column vector. But again, if that's kind of seems confusing, just forget it and just use the notation that this uv angle bracket with a line in between is meant to be the literal dot product between the two vectors. Okay. So the nice thing about this is that it allows us to rewrite the third law in a mathematically nicer form. Okay, so what do I mean? So we know that the probability is proportional to the length of projection of psi along the direction u. And since psi and u are unit vectors, the length of the projection is the inner product between them, which we can denote as this guy. Okay, so it happens with probability, the inner product between u and psi, and the other event happens with probability, the inner product between v and psi squared. Okay, so computationally, and if you want to just sort of keep quiet and calculate and use the laws of quantum mechanics without questioning, you just have to compute these inner products over and over. Okay, and the inner products dictate the probability of each one. Okay, the nice thing here is that you don't have to, every time I give you two new orthonormal vectors, you don't have to figure out like what's the length of the projection. It's always the same formula. So you compute the dot product between them, square it, that will tell you the probability of one outcome and then the other. Okay, any questions about this? No, all good? Okay. Now, let's talk about higher dimensional, like, multiple qubits. So far we've been talking about a single qubit, right? Or single photon. It's denoted by, it's either in horizontal polarization or in vertical polarization. So you have some point, alpha and beta. There's alpha times 0 plus beta times 1. So this was our qubit. Okay, but now imagine I build a system with 2 photons. I think people use some notation like this. I can never draw it too well, but let's say I have another photon. Let me call it, psi 1, psi 2. Okay, so now I have 2 photons. Okay, so when you put the 2 together, right, how many options are there? Again, think of like, classical. If I have 2 bits, how many options are there for both of them together? There are 4 options, right? The first one could be in horizontal, the second one could be in horizontal, the first one is horizontal, the second one is vertical, and so on and so forth. Okay, so we have 4 options. And there's a natural generalization of the system for a single qubit to higher things, right? You remember the first law said, if you have 2 options, your system can be in a superposition of those 2 options, right? If I put these 2 together, I have 4 options, 2 for each. So the natural extension that the system can be in a superposition of all of those 4 things. Okay, quantum mechanics, it's definitely very counterintuitive to common sense, but the math, for the most part, your natural guess will work. Okay, especially when you talk about like you're dealing with amplitudes, whatever seems natural will actually be the truth. Okay, so the new quantum mechanical law 1 would be that if a system has d options, let's say 1, 2, so on up to d, then it can be in a superposition of all of them. Okay, meaning the state will be described by d numbers now. Okay, and you still have the same important property that the sum of the squares of this amplitudes is actually 1. Okay, so sum of squares of the amplitudes, is 1. So as an example, if you have 2 photons in your device, then how many options do we have? We said we have 4 options, right? And here's where I think the bracket notation is very useful. When you put multiple qubits together, you kind of denote the multiple options by the bit strings. Okay, so we have 4 options. Instead of calling them 1, 2, 3, 4, we call them 0, 0, 0, 1, 1, 0, and 1, 1. Okay, intuitively, you once again are saying something like, okay, the first photon is in state 0, the second one is in state 0, or something like that. Okay, but you should never say it is in state 0. You should say the amplitude is something. Okay, so if I say the combined state of a 2-qubit quantum computer or 2-qubit system would be, we'll say alpha 0, 0 times 0, 0, alpha 0, 1 times 0, 1, plus alpha 1, 0 times 1, 0, plus alpha 1, 1 times 1, 1. Okay, to describe a 2-qubit system, you need 4 numbers. All right, so you have same thing as before. All of these numbers would add up. The squares would add up to 1. Yeah.
Is one of the challenges of getting a sort of high qubit physical systems implemented the difficulty of this explosion of being able to distinguish between each of these alphas as you raise the number of qubits?
Not necessarily. I don't think that's the main challenge. The main challenge is really to, so this setup is really assuming there are only 2 photons in the device. Okay, so the main challenge is making sure that there are only 2 photons and there's nothing else interfering with your life. Okay, that's the most important challenge. This explosion and everything, that's fine, right? Because as in, our nature is giving us lemonade. Nature is giving us, if you have 2 photons, it has these 4 numbers in there. You're trying to use it. But the problem is, of course, that there's a lot of junk, which kind of interferes with it. It's extremely fragile and sensitive. So we have to be careful with that. Okay, that's the experimental and physical challenge. Okay? But in terms of description, it's just these 4 numbers that describe the 2-qubit system. Yeah?
Can you explain again what the semantic meaning behind the cat notation 00 is? Like, how does that account for the fact that the photon itself can be in a superposition as well?
Right. So remember, when we said 0, that corresponded to really to amplitude 1 on 0 and amplitude 0 on 1. Right. So we always have this alpha squared plus beta squared is 1. Okay. And the same thing here. We have 4 numbers, their squares add up. Right. If I say it's 0 and 0, that's a state. That just means that I have amplitude 1 on 0, 0 and 0 on all of the other 3 possibilities.
So like you could compose, like using the alpha 0, 1, alpha 1, 0, you can compose like a certain magnitude on each.
Yeah, it's as long as the number of squares add up to 1, that's a valid state. Okay. And I mean, the ket notation is useful, is as I said, you could just call these things, vector 1, vector 2, vector 3, vector 4, but we associate these things because that's how we're going to perform operations. Yeah.
So does it do the same collapses to 1 of the 4 states, but this just kind of describes it?
No, not necessarily. It can actually be in a superposition of all of these things. It will only collapse if we do something to it. If you do any measurement or something, that's when it will collapse. Okay. Again, nature gave us this amazing power that when I put these two photons together and do something, it can and will be in superposition in all of these four possibilities. It's just like a single qubit. There are two options. It can be in a superposition. If there are two photons, there are four options. It can be in a superposition of all four of them. Okay. Any questions? So where we are heading towards is just generalizing one law to the other from single qubit to multiple qubits. Okay. So what is QM law 2? Right. So recall, we said if you have a state alpha times 0 plus beta times 1, if I measured it in 0, 1, then the first event happened with probability alpha squared, the second event happened with probability beta squared. Okay. The same thing, how would you generalize it to D things? So let's say I have a state, which is alpha 1 times 1 plus alpha 2 times 2 plus alpha D times D. If we measure in what's called the standard basis, this is the analog of the horizontal polarization measurement device. Maybe I'll denote it like you have 1 to up to D. Okay. So what would happen if I send my state through this device? As I said, take your natural guess, it will be right. What do you think should happen when I send this new qubit through this measurement device? Yeah?
We'll get a one-time probability alpha.
Exactly. It's going to collapse into state 1 with probability alpha 1 squared, state 2 with probability alpha 2 squared, state D with probability alpha D squared. Okay. So, if you specialize it to a system with 2 photons, then you'll say if I measure it in the standard basis, they will be in horizontal with probability alpha 0, 0 squared. They'll be horizontal vertical with probability alpha 0, 1 squared, and so on. Okay. All right. Any
No, my
questions?
computer blue screen that reinstalled graphics.
All right. Okay.
Or reinstall it.
Finally,
Graphics
we need
card driver
quantum
or
mechanics
whatever.
law 3, which is
The driver
where the gates will
last
come.
year.
So earlier we said, you can implement nature allows us this ability to build a device
Oh
for
no,
rotating any
they
state.
were like,
It
it
allowed
happened.
us the ability to hold on. Someone is. It allowed us the ability to reflect along any line. Okay. More generally, for whatever reason, just 1 second, nature allows us this remarkable ability to build a device for any linear transformation. That preserves lengths. As long as you have a linear function such that for every vector v, or for every vector psi, the length of psi is exactly equal to the length of applying the transformation. You can build a device for it. Okay. We can build a device. So that's the real, let me use, power of quantum mechanics that we're going to explore, right? For a single qubit, we saw that, for every rotation, we could do a device. that already allowed us to do something impossible, seemingly impossible, right? We could detect whether there's a bomb with tiny probability of explosion. Now, more generally, if a multi-qubit thing, as long as you have something which is preserving lengths, you can build a device for it. So that what comes out is exactly applying this transformation. Okay. And what we'll do in next class is look at examples of these transformations. And when you have 2 qubits or 3 qubits, that's all we really need. Okay, so as long as you have 3 qubits or D is like 8, that's enough to do quantum computing. And these devices are what make up gates. Okay. Again, we'll only need 2 gates, the quantum NAND and the Hadamard gate. But the abstraction is the nature allows us to build any of these devices. The dimension is small, the cost is just a constant, and we put these things together to build our circuits. Okay. All right. So I'll stop here, and I'll see you all on Wednesday. And remember to fill out the feedback forms.
When you say feedback forms, is that a quiz you made or like the
The official evaluation, sorry. The official evaluations.